thank you all for coming here to the physics colloquium talk. Today, it's my pleasure to introduce you to our colloquium speaker today, Professor Katerina Chatziioannou from Caltech. So first of all, let me just say a few words about her professional trajectory. Katerina did her PhD at Montana State University on general relativity and gravitation. After that, she was a postdoc researcher first at the Canadian Institute for Theoretical Astrophysics, and then at the Center for Computational Astrophysics at the Flatiron Institute in New York. And then after 2020, she started as an assistant professor at Caltech and was recently awarded a prestigious Alfred P. Sloan Research Fellow. Katerina is an expert on anything related to general relativity and compact objects. She's a member of the LIGO-Virgo-Cagra collaboration, and also more recently a member of the nanograph collaboration, the pulsar timing array. Two weeks ago, we already heard from our own Geoff Pennington about what would happen to an isolated black hole in an ideal universe, perhaps over eons until the end of time, according to the laws of quantum mechanics and general relativity. That's fascinating. But today, Katerina will continue that story and tell us instead what happens to more realistic black holes in this universe over this Hubble time, how the black holes, I guess, find each other in pairs, and in particular, what can we learn from the spin of the black holes, which is one of the important properties according to the no-hair theorem. Okay, I think that's going to be a very exciting topic, and I intend to waste no more time. And now I'm handing the microphone to Katerina.
The wireless, thank you. Will you turn off lights? Okay, yeah, thank you. Thanks for the invitation. As Liang said, my research is on general relativity and gravitational waves. The full universe of gravitational waves is, of course, an exciting new tool that we can use, and just like electromagnetic waves, gravitational waves come in different frequencies. Again, just like electromagnetic waves, we built different detectors to detect different frequencies, different astrophysical sources out there emit at different frequencies. And I think over the course of the visit today, I've had discussions with people here about every single of these spectrum categories and detectors for gravitational waves. In this talk, what I will be focusing on, because we can't cover everything, is the far right side, so the ground-based detectors that detect gravitational waves at frequencies of tens to hundreds of hertz. The most sensitive of which are, of course, the twin LIGO detectors, LIGO Hanford in Washington, and LIGO Livingston in Louisiana, that are today routinely detecting gravitational waves from merging black holes and neutron stars. The schematic here shows you sort of the collection of black holes and neutron stars we have seen with gravitational waves detected by LIGO, Virgo, and Cagra. The y-axis is the mass in solar masses. The x-axis is uninteresting, doesn't matter, we've just ordered them somehow. But the blue colors show you the black holes we have detected, and the orange show you the neutron stars we have detected. The way to understand each of these is we're detecting objects in a binary. So two objects, in this case, two neutron stars, came together, merged, and gave one final object, which in this case is shaded orange and blue, so it could be either a black hole or a neutron star. So we're detecting those objects in binaries, either binaries of black holes or neutron stars or combinations of them. And a lot of my work has been on understanding the properties of the neutron star, so what happens down in this 1 to 2 solar mass range, and I know there's also work here on understanding what happens after the neutron stars merge. That's the good news. The bad news is that we haven't had detection of these in a very long time. So instead of talking about neutron stars, I'll talk about black holes. You see, we have a lot more black holes than neutron stars, a lot more blue than orange in this picture. So I will talk about black holes, which are also very exciting from multiple fronts. We can use those black holes to do astrophysics, such that, for example, we can ask questions about where the black holes come from. Black holes also in binaries exhibit very interesting relativistic dynamics, and especially when the spin of black holes is concerned, which is going to be the main focus of my talk, there's a lot of detail in how the spins interact, especially as black holes merge, that we don't really understand. And also something that I had a lot of discussions about today, the spin of black holes plays a key role in processes like superradiance if you want to detect axions around black holes. So what we'll be talking about today is the blue objects and what we can do with the spins of the black holes, what we can measure, what does it mean, how sure we are our conclusions are correct. Okay, that's sort of the broad picture. Let's take a step back to describe a lot of what that is. This is what a black hole would look like over the Bay Area. This is a nice app by one of our colleagues called Dan Wysocki. Go here and put a black hole over wherever you want. That is a 30 solar mass black hole, which is sort of most of the black holes that we're detecting. Its size is a few hundred kilometers in size, so if you place it over the Bay Area, it's going to cast a huge shadow. But the point is, it's not that it's huge. The point is it's small. We have 30 solar masses worth of energy down to a very small region of just a few hundreds of kilometers. That's a very large concentration of energy. And in order to detect that very large concentration of energy, we use gravitational waves. The first detection of gravitational waves, the first direct detection from a collision of two black holes happened in 2016. 2015 for the signal, 2016 for the announcement. And since then, it's been almost 10 years now. But I guess to some extent, maybe black holes and gravitational waves especially haven't found their way to the standard undergrad curriculum. So I want to give you a little bit of an introduction, what gravitational waves are. And I'm going to give you two introductions of slightly increasing complexity. So first of all, this is going to be a simulation. It's going to play in a second that shows two black holes orbiting around each other. And as they orbit around each other, they emit energy in gravitational waves. These are going to be the colorful ripples you're going to see in a second. And this kind of simulation of what happens when two black holes merge, you can only perform on a computer by solving the full Einstein equations extremely carefully. Okay, so when two black holes go around each other, they lose energy, and that energy is the gravitational waves that are produced by some of the most violent events. You need that much energy packed down to that little separation in order to produce strong gravitational waves, such as the collision of black holes. And they're emitted exactly by the motion of the black holes. As the black holes move around each other, as the energy moves around, that's what produces gravitational waves. Gravitational waves travel at the speed of light, at least when they're propagating in flat space-time, and they mostly travel unimpeded through anything. They're not like light that gets trapped easily. Gravitational waves just propagate through. And the way we measure them is by their impact on objects here on Earth. So when a gravitational wave passes through Earth, the distance between object changes, and this is what we're tracking. The simulation gets close to merger because it has emitted a lot of energy. The black holes get close together. It's going to slow down in a second. And let's admire the very last stages. It has slowed down at this point. Now it has frozen. And the black holes almost peacefully join together. And that event that looked so nice and peaceful emitted so much energy, so much luminosity that essentially outshines the entire universe, the entire rest of the universe put together. Okay, let's talk a little bit about gravitational waves now in a slightly more complex fashion. This is what you would find in an introductory general relativity course. And this is going to be, fair warning, the only slide with equations. So after that, we're done. Okay, so what are gravitational waves? We have this picture of energy emitted outside the binary and ripples in space-time. Yeah, sure. Actually, what happens is that it's a wave equation. Same way electromagnetic waves are, you take Maxwell's equations and manipulate them and get out a wave equation. Gravitational waves are kind of similar. You take Einstein's equations, you manipulate them, do a lot of math, are very careful about gauges and stuff, but you end up with a wave equation. And the wave equation is for the space-time metric. The space-time metric oscillates like a wave, and that solution propagates away from a source. If you do a quick estimate of what causes gravitational waves, the answer is quadrupole moments. In electromagnetic theory, electromagnetic waves are created by changing dipole moments. This is general relativity, so everything's going to be a little bit more complicated. So instead of changing dipole moments, you have changing quadrupole moments. So you have the second time derivative of the quadrupole, and like any respectable wave, it goes as 1 over r, 1 over the distance to the source. Their amplitude is extremely small. If you do an order of magnitude estimate about the amplitude for the gravitational wave emitted by the merger of two black holes is about 10 to the minus 21. That is a dimensionless number. It doesn't have units, so take it as is, 10 to the minus 21. It's tiny. Their spectrum goes as about 1 over the mass. So that's mostly how we measure the masses of the objects that merge. We measure the frequency of the wave, and from that get the mass of the wave. They emit huge amounts of energy. Nothing like anything we can think of terrestrially. Any event that includes black holes with masses like the ones that LIGO sees will emit a total of some number of solar masses worth of energy. And it's not just a lot of energy, but it also does it in a very small amount of time. So energy divided by time is luminosity, and the luminosity of those events is 10 to the 56 ergs per second. It's huge luminosity, more luminous than anything else in the universe, which is funny to think that we just detected those objects just 10 years ago, but it's what happens. Okay. So the first detection was 10 years ago, and since then a lot has happened. The progress in the field is actually accelerating. It's not just that we're detecting more events, we're detecting them at an increased pace. The plot here, the y-axis, is think of it as the number of detections, and the x-axis is time. And the blue is how quickly we were detecting events in the previous observing run, so back in 2019, and the more pinkish white color is how quickly we are detecting them today. The slope of that curve basically tells you that we're detecting events faster, and that is thanks to detector improvements. And the detectors are becoming more and more sensitive as work is done to improve their sensitivity as they go through cycles of commissioning, upgrades, and observation, which allows us to detect events at a more accelerating pace every time they come back online. Our sensitivity is basically 1 over the distance to the source. So the number of events that we detect goes as the volume that we can probe. So an improvement in the detector sensitivity really gives us an R-cubed improvement in how many events we are detecting. Okay, so let's talk about then what we are measuring as I'm making my way into the spins of black holes. We're detecting something like the following. The signal that we are observing looks something like this. Like any wave, it oscillates, but it also has specific stages. So early on, you have the in-spiral, what we call the in-spiral. You have 2 distinct black holes orbiting around each other, and you have a nice sinusoidal modulation of the signal. From that stage, we measure things like the masses and the spins. From the frequency of the signal, we track the phase, we measure masses and spins. While from the amplitude of the signal, how strong it is, we measure the distance to the source, because it goes as 1 over the distance. Eventually, it's going to emit so much energy that the black holes merge together. This is the merger phase. Now, this is what's happening in the simulation. The stage where the black holes are very close and are merging. And at the end, you have one final black hole ringing down into its steady state by emitting additional radiation. So this is the signal we are detecting, and this is the signal that we have to use to learn about the properties and dynamics of black holes. The first thing you, of course, measure is the mass. This is a gravity experiment, so the dominant thing we measure is the black hole mass. The plot here is a result that we obtained as part of the LIGO scientific collaboration. The specific kind of choice of visualization was performed by Jacob Gollum, who's a grad student at Caltech, but this is a result from the LIGO collaboration that shows the mass distribution of black holes. So you have two kind of, you have a kind of shading. The shading gives you an estimate of the uncertainty. For example, look at the yellow shading. It's an estimate of the uncertainty. The x-axis is the black hole, the primary black hole in the binary, and the y-axis gives you the rate. How many, essentially, read of it, how many black holes we have at a different mass. I'm showing two sets of results here, just again to give you an idea of how fast progress is in the field. The white is what you had from the second observing run, where we had detected 10 binary black holes. That was 2017. The yellow is from the third observing run with 70 black holes, 2019. So in 2 years, we have an additional 60 black holes, and you see what that does to our uncertainties, how much smaller our uncertainties are in just 2 years. And we have more data in the pipeline. Okay, so this is the result about black holes we're computing. You can use that to do all sorts of interesting astrophysics, and astrophysicists have spent a lot of time trying to interpret various features, like maybe there's a peak here, maybe there's a peak here, there is no cutoff, no kind of maximum black hole mass that we're detecting. Oops. But this is the kind of games we play with the mass of the black hole. What I instead want to talk about is not so much the mass, it's the spin, because one of the various reasons. The black hole mass is well measured, we can make this distribution, we can measure it. But the mass of the black hole is kind of more straightforward, and it also doesn't tell you as much about the astrophysics of black holes or the interesting dynamics, relativistic dynamics of black holes. On the astrophysics side, one of the big questions that we kind of use as a motivation to hone in on spins is the question of where those black holes came from. And there's, roughly speaking, there are two sort of ideas. On the left side is that those black holes in binaries have basically spent their entire lives together. They start as two stars, like our sun, bigger than our sun, in a binary. Actually, our sun is more the exception rather than the rule, being alone. A lot of stars are in binaries. So those two stars evolve together all the way through the main sequence down to a black hole, and that down here is what we're detecting. This process takes giga-years. The other idea is that there's some kind of dynamical formation in a very dense environment where a star or a black hole randomly finds another black hole and captures it in a binary and merges. This happens in very dense environments out there called clusters. In a star like our sun, this is not going to happen to it. It's not going to randomly find another star because it's not in a dense environment. But there are black holes in dense environments where this can happen. This is a very simplistic picture. In reality, there's a lot more kind of formation scenarios, but this is not what I'll be talking about, the formation scenarios. Rather, we're using this as a more of a motivation as a further motivation to understand black hole spins and go to black hole spins. So like any other object, black holes have a spin. The interpretation is not the same as a rotating, a moment of inertia, et cetera, but there's a property for black holes that we call a spin. And when you have two black holes in a binary, you have two spins, one per black hole, for a total of 6 degrees of freedom. That's a lot of stuff going on. Okay, so what happens when two black holes spin and they merge and emit gravitational waves? Roughly speaking, there's two physical phenomena at play. The first is the top here, what I'm calling the aligned spin. So essentially, think of a binary. Two black holes go around each other. There's an orbital angular momentum pointing up, and then you have some spin that is parallel, pointing either in the direction of the orbital angular momentum or opposite direction of the orbital angular momentum. So basically, think of the spin that is parallel or anti-parallel to the orbit. So this is what happens as you change that spin. The schematic here shows you a binary. It's going around in this direction, and the vector shows you the amount of spin. So you go from here very anti-aligned spin to 0 to here very aligned spin pointing in the same direction as the orbital angular momentum. And you immediately see what happens to the signal. What happens is the length of the signal changes. The basic physics at play here is that you have more angular momentum in the binary. So if you have more angular momentum when the spin is pointing up, you need to emit all that energy and all that angular momentum before you merge. So the waveform is longer. The signal takes longer. The binary takes longer to merge, so the signal is longer. So this is what aligned spins do to you. But there's another kind of configuration where you have misaligned spins, basically spins pointing perpendicular to the orbital angular momentum. And so let's see what happens here. This is more interesting, isn't it? So instead of the length of the signal changes, what happens here is the signal has those interesting amplitude modulations. It's not that its frequency changes or that its length changes, but the amplitude is modulated. Physically, what happens is you have precession. This is a simulation of numerical simulations of two black holes with misaligned spins. And you see that what happens is the orbit does not evolve in a single plane, but instead tumbles around in space. And gravitational waves are not as directional as a gamma ray burst, but they have some amount of directionality nonetheless. So when the binary changes orientation with respect to how you see it, sometimes you see it when it emits a lot of energy from a direction that a lot of energy is coming out from. And sometimes, because it precesses away, you see it from a direction without as much energy, so you see it at a low of the gravitational amplitude. So this is what we're seeing. This is called precession. And it's a general relativistic effect that comes from the fact that the spins of the black holes are also interacting and are causing the binary to change orientation in space. And that, again, is observable, and we can try to measure it. OK, so let's, why is this so interesting? Basically, from the astrophysics side, there seems to be some kind of simple-ish delineation where the two formation scenarios predict slightly different spin configurations. For the isolated evolution, because the black holes have spent giga-years together, the spins have essentially aligned due to dynamical friction, so the spins are pointing up. But if the binaries form randomly in a dense environment, the spins can be pointing in any direction. So motivated by this, we are, to some extent, looking for anti-aligned or precessing spins, because those are the ones that tell us that something dynamically, something interesting happened in the binaries shortly before we observed it, shortly before it merged. So it has more interesting spin dynamics and spin directions for us to probe. And that's the kind of good picture. The downside is that this is a very difficult measurement to make. Roughly speaking, we measure the masses much, much better than we measure the amount of aligned spin. And that is much, much more easy to measure than the amount of precessing spin. Just a rough idea for why this is, it's because the mass comes from the frequency, which is easier to measure than the length, which is how we measure aligned spin, which is much, much easier to measure than a slight modulation in the amplitude of a signal, which is how we measure precessing spins. Obviously, the picture is not as simple. Like, there are a lot of degeneracies in this mapping and how you measure things. It's much more complicated. But just a rough idea for how we measure each of these effects and why there is this very clear scaling of what is more easy and what is more difficult to measure. So the interesting spins that we want to measure are difficult because, intrinsically, it's a very weak imprint on the signal. So let's see what we have. Here are some results from observations, again, obtained through the LIGO collaboration. On the y-axis is the amount of aligned spin, and on the x-axis is the mass of the primary black hole in the binary. And the different colors show you some of the events that we have detected, a subset of them, not all of them, but a representative subset. So the way to read this plot, the x-axis is simple, it's just the mass. The y-axis is a spin, so 0 means no spin, no aligned spin at least. +1 means maximum spin pointing up, so pointing along the angular momentum, and -1 means maximal spin pointing down, so the opposite direction of the orbital angular momentum in the right-handed sense in which the binary is orbiting. Okay, that's sort of some of the measurements, and you immediately see kind of the problem is that the vast majority of our detections don't seem to have much spin. Most of them are consistent with zero spin, which is not great when you want to understand, the dynamics of spins, when you want to do any astrophysics with the spins. It would be good if it had some more spins. But there are some exceptions. Some of them are spinning, but they are, unfortunately, the exception. In fact, this is sort of general what we're finding. Most of them seem to have, at least are consistent with vanishing spin. But we do have few and far between exceptions that are more exciting events. Let's look at one of them in more detail. This is GW190521, and it is the heaviest of them all, the heaviest event that we have seen at a total mass of 150 solar masses. Because it is so heavy, it has a very low frequency, which means it's an extremely short signal. This is what it looks like. Remember those nice plots with a long in spiral and merger? Nothing like that. Because the mass is so large, we only see 3 cycles for this event. This is what we observe in one of the 2 LIGO detectors. The colors here, bluish is the gravitational wave signal, and the yellowish is the data. And because of all this variation in the data here, this is noise. And then out here is when the signal is. Extremely short signal. The fact that it is low frequency and short signal is exactly what tells us that we have only detected the merger portion. What we're seeing here is 2 black holes that are just about to merge and merging. And that tells us it's a high mass signal at the record holder, current record holder at 150 solar masses. Okay, so when you see an event like this, and I've told you that spins you measure from the length of the waveform or from modulations in the waveform, you would assume that spins are completely unmeasurable. We don't measure them for most events if you have a long signal. How can you measure it here? Well, you would be surprised, and we were very surprised. Because you can actually measure, you can place some constraint on the spin of the black hole. So the plot here shows you on the y-axis the amount of aligned spin, where again, +1 means pointing up, -1 means pointing down. And the x-axis is the amount of precessing spin. So 1 out here, you have a lot of spin in the plane of the binary. So the yellow is the measurement for this event. The white is the prior you use for the analysis. So it's essentially uninformative. For the vast majority of signals that we're detecting, the white is essentially what we measure as well. We have no constraints. For this case, we actually do have something. We have some constraints on the spin of this black hole and the amount of precessing spin that this binary has. And this has generated some excitement also in the astrophysics community, because the combination of high mass plus precession has led people to argue that that binary has a very specific and rare origin story. I'm not going to go into details about this picture, but the point is that we have this measurement. It has a unique and rare spin measurement, and this has a very influential astrophysical conclusion. So the question is that the thing that I want to hone in more is, how do you actually make that measurement? When you have 2 black holes that are merging, how can you measure the spins of those black holes? So let me take a second then to describe how we measure things. The process uses something called, in various fields come with different names, we typically call them forward models, where you have some parameters for the binary, say some masses and some spins, and given some parameters, you predict what the signal should be as observed by the detectors. You compare that signal to your data and figure out if those parameters were correct. Gravitational wave science with black holes has essentially perfect forward models. I don't know if there's any other field in astrophysics or physics that can say this, but when you have vacuum general relativity with just 2 black holes merging under just the theory of general relativity, you can put those in equations in a computer and solve them exactly. And to the best of our understanding, there is no missing physics here. It's just general relativity, to within numerical error, obviously, in the simulations. This is not the case, obviously, when neutron stars are merging. There's so much complication in the physics there that you have to worry about. But when you're talking about black holes merging, you can just put the whole system in a computer and it just gives you the answer with no missing physics. the good news. The bad news is at the same time, you're solving extremely complicated, nonlinear dynamical equations. And at the end, you get out a line, a number for the gravitational wave signal. So there's as much physical intuition for what goes on. How did the spins exactly affect the signal out here in the merger? You have such a complicated systems. You put in a computer, an answer comes out. It's not clear how exactly the spins of the black holes caused the signal to look like the way you detected it. So we can make those measurements using the forward models. We can compare them to the data and make the measurements. But it's not clear how we actually made that inference, especially when you have such short signals when you only see the merger. So one of the things that I want to understand better is how morphologically we make those measurements. Precession is a slight modulation in the amplitude. I don't see any modulation in the amplitude. I just see a merger here. And it's not clear how you measure precession. So I want to understand this better. And especially when you're making a very subtle measurement, I think it is important to understand how you made that measurement, morphologically how you made that measurement, how the data you used told you what you have. Okay, so what we did is a study led by a grad student at Caltech, Simona Miller, who took the data and essentially split it into half and measured the parameters before and the parameters after. So if you only use a subset of the data and compare it to what the whole data gives you, you might get an indication of which part of the data is more important for the measurement you're trying to make. So let's look at the result. This is a GIF that's going to play in a second, but I want to explain what it is before I start playing it, because it's going to be complicated. Okay, so on the left is the amount of precessing spin. The white dotted is the prior, which means no information. The white solid is what we get from the data. So there's some information there. And then Simona took the data and analyzed before and after. Before is always yellow, after is blue. What is before and after? Look here, what is before and after. Yellow means we're analyzing only that data, so nothing really happens, right? You have no data. You don't expect to measure anything, so you get the same as the prior. Blue is the after, and it's basically here the entire signal, so you measure something nice, and that looks like what you would expect from the full data. So let's play that. Each step essentially changes what data you're analyzing, and I'm going to loop it around, play it a couple of times. But you see the step size, how much data you are analyzing changes. And what you infer about the spins also changes. Look from the beginning, you see initially the blue looks like you've made a measurement, and then somewhere around here, it completely loses a measurement, which tells you something is happening in the very early stages to give you a spin measurement. Now, let's focus in more on this, on what happens, how you have measured it. To understand what we have measured is we've looked at two different subsets of the data, one that has no measurement, the blue, and one that has a measurement, the white, and compare what the signal looks like in those two different instances. So on the right side is the signal. In one case, when you've analyzed it in a situation when you have enough data to make a measurement, and another case when you don't have enough data to make a measurement. And what is the difference? What is the difference in the signal? Where does it come down, making a measurement versus not making a measurement? Is this tiny difference here. The difference between the white and the blue here, which is essentially tiny. The y-axis shows you the noise, so standard deviations compared to the noise. So if you want to measure the spins of black holes in binaries, you need to measure your signal to an amount that is, you need to resolve that tiny amount of difference. Compared to the noise, this is less than 1 sigma on top of the noise. This is the kind of measurement you have to make if you want to measure the spins of black holes. The effect is so subtle that events that we are detecting have such weak imprint of spins that you have to be able to resolve something of the order of much smaller than 1 sigma compared to the noise to make that measurement. It's an extremely subtle effect, especially for those signals that we're detecting that are very dominated by the merger of the two black holes. So just as a first part of the talk, to summarize, I've introduced spins and argued that they carry a lot of information about the black holes, and the imprint of the spins is extremely subtle. If we want to make robust spin measurements to understand the spin dynamics of black holes, to understand how big the spins of black holes are, we have to make a very subtle measurement, a very small change in the signal that tells us how much the black holes are spinning by. So when I tell you have to make a very subtle measurement, and have quantified how subtle, the obvious follow-up question is, well, what could have affected that? What could have affected the measurement and contaminated what you're trying to measure when you're trying to measure spins? So one of the things that could happen, one of those kind of systematics that could creep in when you try to measure spins of black holes, is glitches. The detectors, most of the time, are behaving well, and the noise is nice and Gaussian and clean, but sometimes they experience loud glitches, where essentially you have large amounts of just noise. The plot here is the frequency time decomposition of the data around the first neutron star binary. This was GW170817. And actually, when I first showed this plot to most people, I asked, okay, where's the signal? They would think that this is the signal. This is not the signal. This is the signal, the chirp in the background. This beast here is a massive glitch that happened on top of the signal, this part here. For those who kind of have an estimate of how strong those signals are, the neutron star binary had a signal-to-noise ratio of 32. It was an extremely loud signal. The glitch had a signal-to-noise ratio of 900. It's extremely loud. It's actually called an overflow glitch because it causes an overflow upstream in the detector, not in the gravitational wave channel. But those things happen, and they are bad. Here's another example of a glitch. This is called scattering. It's because light from the laser bounces off, and then if it bounces off a moving surface, it acquires a phase shift, and then when it recombines with the main beam, it has a phase shift, and that causes additional noise. So those things happen, and they're bad, and they're not rare. The plot here is the rate of glitches in Hanford, Livingston, and Virgo throughout the third observing run, and they're about 1 per minute, something like this. So at 1 per minute, when they're constantly happening at 1 per minute, they're not rare, and sometimes they actually overlap with the signals, and that's not rare either. We have about 90 black hole binaries announced and fully analyzed today. 20 of them overlapped with a glitch. That's a fifth, well, a fourth, or one per 4.5 or something. And you might see where this is going. Some of them had a spin measurement. We have 2 more interesting events with evidence for anti-aligned spin, so spin pointing down, or precessing spin, so spin pointing in the plane. Both of them overlapped with a glitch. So we have to make a very subtle spin measurement, and something is going wrong with the noise. Let's look at it in more detail. We conducted 2 studies led by Caltech grad students. The first event was led by Ethan Payne, who looked at one of the events, 200129. The phone number doesn't mean much. But here is that signal in Hanford, Livingston, and Virgo. The signal is here. This is the signal. This kind of maybe a little bit of a chirp. When you look out here in the spectrogram, the data are clean. This is what Gaussian noise more or less looks like. But that's not the whole thing. This is a glitch, but it doesn't overlap with a signal. That's fine. That's not cause a problem. The glitch here causes a problem. That is a glitch. It doesn't look too much like a glitch, but there's auxiliary channels in the detector that tells us that a glitch happened at that time. And guess what? There was a very interesting spin measurement for this event, confirmed both by the LIGO collaboration and independent analysis by Hannum et al., where the figure here is slightly more complicated for spin measurement than I showed before, but essentially the radius shows the magnitude of the spin, and the polar angle shows the direction. So up here, the spins are pointing up and are large. Down here, they're pointing down, and here they're pointing in the plane. And the measurement is concentrated at this point, which means that there's a very strong evidence that there is precession in that system. So extremely exciting system. Very, very good, nice, clean measurement of precession. The problem is it overlaps with a glitch. So we had to look into it in more details. And here is a plot of the data. And after the analysis, what we infer for the data, the blue is the glitch. The bluish color here is the posterior for the glitch. It has some uncertainty. And the green and the pink are the signal. And you see what they're overlapping. That's what I mean, they're overlapping. They happen at the same time. And the difference between the green and the pink is what you have, again, to resolve if you want to measure precession versus non-measure precession. This tiny difference between the green and the orange is what it comes down to when you want to make that measurement for the spins of the black hole. And unfortunately, the green that the glitch that overlaps with it, the blue, has a much, much larger uncertainty. So the width of the blue is much larger than the difference between the green and the pink, which means it's very difficult to make that measurement. And if you ask me if is that event precessing or not, the answer is I don't know. Honestly, we're at the limit of what you can actually measure, what is theoretically possible to measure when you have extremely weak imprints, extremely subtle imprints and imperfections in the data. That's the point where the overlap happens. There's another event, 1911-09, same picture. This is the signal, and it overlaps with some glitch power here. And we had to look into that in more detail as well. That's another study led by Rhiannon Udall. She's a Caltech graduate student who looked into this in more detail. And Rhiannon has spent a lot of time thinking about a certain type of glitch, that's a scattered light glitch. And she used her targeted model for the glitch to understand that signal, figured out that the glitch and the signal overlap down here. And when you try to measure the spin, the good news is that the spin remains negative. This is the amount of aligned spin. 0 is here. I don't know if you can see the orange line appearing. And it's still strongly negative. So this is what happens when you understand that type of glitch and model it very well. We have more analysis because we are really interested in glitches. And another grad student at Caltech, exactly because it has a lot of implications for what this kind of signal would be. Another grad student at Caltech, Sophie Hurrihan, has a more flexible glitch model, more phenomenological. Glitches are not binary black holes where you can model them without any missing physics. You have to be worried about your models. Sophie has a more phenomenological glitch model, and when she applies that on the data, she gets a much larger uncertainty for what the glitch is. And worryingly, she ends up with the conclusion that there isn't any anti-aligned spin. The spin is not negative, it's consistent with 0. This is a problem. If you ask me again, is that spin positive or negative? The answer is I don't know. It's almost unknowable when you have so much uncertainty in what generates the noise on the detectors. Measuring that kind of, making that kind of weak measurement is almost at the level of fundamentally impossible. So this is one of the kind of problems when you want to try to measure spins. They have a very weak imprint on the signal, and they can be affected, majorly affected, by any noise imperfection. Okay, this was the second part of my talk, and I have one final thing I want to talk to you about, because maybe so far with all the discussion about glitches and noise imperfection, everyone thinks this is impossible and it's depressed. So let's end with on the positive side. Some stuff we can actually measure and I think are robust against even these kind of uncertainties. What can we actually say about spins, the spins of black holes? Okay, so we can look at, for example, what happens in the spins of black holes out there in the universe. So moving away from looking at specific events, but let's look at the collection of all events in the universe. I'm going to start with some results from the LIGO collaboration, and then I'm going to hone in on some specific questions we want to answer as part of our work. The first thing we want to do is how much aligned spin there is. The plot here shows you the distribution of aligned spin in the universe. The blue lines are basically draws from the posterior, different kind of samples from the posterior give you an idea for the uncertainty. And we can draw some conclusions. Again, this is work done by the LIGO collaboration. 0 means no aligned spin, positive and negative means spins up and down. And you immediately see that the spins are not isotropic, there's definitely more positive than negative. A lot of them are zero, but there's more positive than negative, which seems to suggest that the multiple origin scenarios for the black holes at play. Astrophysicists who make those origin scenarios, how black holes are formed, tell me this is a bit surprising, that you would have a lot of them at play, but this is what we're finding. The spins are not isotropic. They have more positive than negative. The amount of precessing spin is shown here. The x-axis is the precessing spin. 0 would mean no precession. And we do have some precessing spins. I did cast some doubt on whether those measurements are robust or not for individual events. But when you look at the aggregate of all events, some are definitely precessing. We get that because the distribution is not consistent with 0 out here. If you look at individual spins, this is what you care if you want to, for example, do superradiance. You want the spin magnitude. You don't want the specific direction in any kind of configuration. You want the magnitude of the spin of the black holes. So in that case, things are more complicated, and there are a lot of kind of studies out there that agree on some things, disagree on some things. I want to start with what they agree on, and then I will go to some of our conclusions for the things that require more careful follow-up. So what have we learned about the spins of black holes? First of all, they're not all 0. That's good. If you want to study spin dynamics and they end up being all 0, you're kind of out of luck. They're not all maximal. This is not something we knew before we started doing those observations, and most of them are low. They have spins around 0.2. An additional question we wanted to ask is, do most black holes have 0 spins? This question might sound trivial, but it's interesting both astrophysically from a stellar evolution perspective, but it's also interesting from a fundamental physics perspective if you want to understand if some superradiance process has caused your black hole to have a 0 spin, to be born with a 0 spin, exactly 0 spin. So if you see them to stellar evolution sometimes predict vanishing black hole spins, that would be really bad news because you can't really do any general relativistic dynamics with vanishing black hole spins. But we want to figure out if the spins of black holes are 0. And that was a targeted analysis led by Simona Miller, where they especially try to answer that question. Do you have an overabundance of black holes at 0? And the answer is no. If you want to measure how many black holes have a spin of exactly 0, the answer is that's consistent with 0. So this is the 0 spin population. How many black holes have exactly a spin of 0? That peaks at 0. There's no evidence that most black holes have 0 spin. That's good news if you want to study the spin dynamics of black holes. That's probably bad news if you want to detect axions with superradiance with black holes. I want to just leave this here without discussing it too much, but I want to caution that these are difficult measurements to make. You have 100 measurements that are mostly uninformative, individually uninformative, because each of the events doesn't give you much information, and you're trying to combine them to figure out if something is exactly 0. You have 100 measurements that are between 0 and 1, and you say, are they all 0? This is technically challenging, and we've put in a lot of work, and people have put in a lot of work, and we need to put in more work to make sure that measurement is robust. How exactly you do this calculation. Okay, the next thing I want to discuss is the spin direction. This would be the cosine of the spin. So essentially 1 means cosine is 1, spin is pointing up. 0 means it's pointing in the plane. -1 means it's pointing down. And what have we learned? We've learned that not all the spins are aligned. This is, again, not something that we would necessarily have expected before we started making gravitational wave detections. There's a wide range of misalignment. Some are 1, some are 0, some are 0.4. So you can have different kind of directions in the spins of black holes. And you have more positive than negative. It's not clear how much more positive than negative. That's a question there's a lot of disagreement about. But there's definitely more spins pointing up than spins pointing down for black holes. So again, trying to get more into the details of this, one of the questions that we wanted to figure out is if you have negative misalignments. Negative misalignments means spins pointing down. I showed you earlier an event with a negative spin, but then I sort of said that, well, there's a glitch, so we're not sure if that's accurate. But now we want to look on the aggregate of all detections if there is evidence for a negative spin for black holes, if you have spins pointing down. This is what the kind of spin you would expect in this kind of very dense environment where the spins are interacting and they're pointing in all sorts of random directions. So this was, again, study done by, led by Simona Miller. And the answer they concluded is that, yes, you have spins you have black holes with spins pointing down. You have this kind of interesting negative misaligned spins because Simona tried to measure the lower amount of misalignment you can have. And that is this point here. That is definitely negative. That's below 0, which means you do have the minimum direction for the spins of the black hole is definitely negative. You have black holes pointing with spins pointing down compared to the orbital angular momentum. Okay, so this was the last part of my talk to discuss basically the range of black hole spin magnitudes and misalignments. Most of our black holes have small spins, but not 0. There is some spin there, which is good if we want to understand their dynamics, and have a wide range of misalignments. That again is good news because it gives rise to this kind of interesting precession dynamics that we're going to measure. Okay, last thing I want to say is that everything I discussed was based on data up to here, so about 100 binary black hole detections. We are currently collecting more data in the 4th observing run. We are making about 1 detection every 2 days. So the total number of detections is up to something like 300 right now, compared to 90 or so that I've shown results for. So I hope everyone is excited for much, much smaller uncertainties in like a year or so. And yeah, I'll conclude here and take any questions. Thank you.
Questions for Katerina? Yes.
I'm just wondering what the event horizon of a spinning black hole would look like. If there's no spin, it's just a sphere. So what happens to the event horizon when it's spinning? In particular, it ends at 1. I saw on your graph. There was a maximum possible spin. What happens as you report the maximum spin to the event horizon?
Oh, for an isolated black hole?
Yes.
Yeah, for an isolated black hole, essentially the reason you end up at 1, the singularity in the black hole is like a ring. It's in the equatorial plane, a ring. And as the spin increases, or the black hole increases, the size of the singularity increases, the horizon decreases, and at 1, the singularity and the horizon coincide. So essentially the singularity flies out of the horizon, and then there's no horizon.
So is it spherical before it flies apart?
The horizon? Yeah.
It's still spherical?
Yeah.
Josh.
Does the auxiliary engineering channels give you a prior on the amplitude of what the glitch is?
Yes.
The phase? So, and you get to make use of those in the analysis?
Yes. The problem is that you still have to estimate some transfer function between the auxiliary channel and the main gravitational wave channel. And there's definitely uncertainties there. The particular auxiliary channel I brought up earlier did provide some information about the origin and the type of that glitch, but we know that I didn't provide the full amount of it because we can compare against other glitches of that magnitude, compare what the transfer channel predicts, what we actually see on the gravitational wave channel without any signal to confuse us. It doesn't predict the full amount. We know that. It gives you some information, but not all of it. And by the way, I should say that noise based on auxiliary channels is subtracted in certain cases where it is possible. Yeah.
I assume that the 2 spins would be going like this, not like this. And in this case, I would call it precession, but I don't know what if you could call this precession.
I'm not sure I get the configuration,
Okay, so
but every time the spins don't point parallel to the orbital angular momentum, you have some amount of precession. In a binary, you have 2 spins. Whichever of the two is not aligned with the orbit, it will cause precession in any kind of configuration, in any kind of angle.
Is the, take one of the black holes, is it going around like this, or is it going around like this?
I'm not sure I understand.
It's spinning.
Yeah.
Is it going around like this, or is it going around like this?
Oh no, yes, there's both the orbit and the spin precess. The spin also changes direction. Yes. So the second, if I understand correctly,
So it's going like this?
uh,
It's going like this?
it doesn't move by that much, but the direction of the spin of the black hole changes as a function of time, but slowly. It doesn't change too fast.
But it's got to change, it's got to change sinusoidally, right?
Yeah,
So
but it's a
maybe-
small
It
oscillation.
wiggles a little bit, but it basically goes like this.
Sort of. It doesn't move as fast, but yes, it does move. Yes.
Okay, so it does move. So which is more? Is it recessing more, or is it, what would you call the other thing? It's what-
Mutation?
Mutation.
Yeah, it's precessing more than it's mutating.
More questions? Yeah.
Did Virgo detect anything? 200, 129. And I saw like a little purple dot thing. But it's-
Yeah. Actually, that is funny because we're not sure if that was a glitch or part of the signal. Virgo has a much higher glitch rate than the two LIGO detectors, and it has an intrinsically lower sensitivity. So it's not clear whether that was part of the signal or not. Yeah, that's one of the other things. Like, again, we're at the limit of what you can actually know. If something has a signal-to-noise ratio of 5, think of it like 4 sigma. It's hard to definitively know what it is, if it's a noise outlier or not. It's an excellent question. And I only showed one of the two detectors. Okay, so here's the problem. The two LIGO detectors in 03, the third observing run, unfortunately did not have the same sensitivity, especially where it mattered. Where it matters is low frequencies, where the black holes are inspiraling, so 30, 40, 50 hertz. And Hanford had a lower sensitivity, and Livingston had more glitches. So Livingston was sensitive and had the glitches. Hanford did not have as many, but it was less sensitive. So it did not have the sensitivity to actually decide that. But that's a very good question. And one of the things in 04 that I'm more optimistic about is that Hanford is doing better.
Maybe let's have one more question, if there's any. Yes.
How do these spin dynamics, like what do the spin dynamics of the black holes tell you about any matter that might be accreting through that system? Since that accreting matter would also possess some angular momentum.
Yeah, so for the black holes that LIGO is detecting, there is probably no matter around them. Those are small black holes that have spent quite a lot of time orbiting around each other, and they are a few kilometers apart, which means they've completely cleared out anything around them by the time LIGO sees them. If you think of something like LISA, the space-based mission, you actually expect matter around the black holes, and for that matter to affect the dynamics. It's going to mostly affect the dynamics by drag, so it's going to slow down the evolution, and that's going to be degenerate with testing general relativity. So people who are interested in testing general relativity have to be really worried about this. The spins themselves, which was particularly your question, it's a small effect, and the angular momentum of the matter probably doesn't matter too much. It's mostly the drag of the matter that would affect the binary.
So Katerina will have maybe 15 minutes before he heads to the airport. But let's all thank her again
Thank you.
for the very nice talk.